And I've got two periodic tables. I'm going to take one, notes on one, and I'm going to use the other one for other reasons. But I just wanted to show you that I have both, even though I can't get them into screen here. Okay, atomic radius increases or decreases as it goes across a period because of, all right. I'm also going to use some other infographic pictures here. Atomic radius, well, does it increase or decrease as I go from left to right? Atomic radius decreases as I go across the period. This is big, this is small. And as it goes across the period, because of being increased, and they pull in electrons. So what am I increasing here? This has 3 protons. This has 9 protons. 9 protons, 3 protons. This has a lot more protons, which is called nuclear charge. And as you add nuclear charge, it pulls the shells in tighter. So atomic radius decreases as it goes across the period because of protons, number of protons being increased, and they pull in the electrons. So that makes sense. Okay, atomic radius increases or decreases, it goes down a group because there is, now I'm going to X out part of this because it's stupid, it doesn't make sense, and that is not what we're paying attention to. It increases as I go down a group because I'm increasing the number of shells. Period 1, period 2, period 3, period 4. By the way, if you don't know these are called periods, then you should fill that in on your periodic table that you're using notes. And I would draw something that has 1 shell. And then draw something that has 2 shells. And then draw something that has 3 shells. So why is it getting bigger? Because of an increase in the number of shells. And I'm going to put an of in here too. Number of shells. That's why it's increasing. Okay. Place them in order from largest to smallest atomic radii. So they want me to do boron and beryllium and lithium in order from largest to smallest. Okay, so the trend for atomic radius on a periodic table is like this. So anything to the left is going to be bigger, anything to the right is going to be smaller. What order? Largest to smallest. So L-I-B-E-B. L-I-B-E-B. As we increase the number of protons, 3, 4, 5, all these have 2 shells. That's where this picture comes in. And look, L-I-B-E-B. Largest, next smallest, because of the number of protons. Why did I place them in this order? Hang on, I gotta adjust my camera here. Why did you place them in this order? Because the atomic radius decreases as number of protons increases. Right? Decreases because the protons increases. Okay, place the following in order from smallest to largest. Okay, let's get our periodic table here. We have Br, Cl, and F. So we have F, Cl, Br. And they want to go from smallest to largest. Well, again, the trend is right here. So anything on top is going to be smallest, anything on bottom is going to be largest. They're talking about fluorine, chlorine, bromine. Fluorine, chlorine, bromine. Why did I place them in this order? Increasing numbers of shells. Increasing number of shells increases diameter or atomic radii. Let's just use the terms they like, or size, or however you want to say it. Atomic radii. All right. From largest to smallest atomic radii. Okay, we have CO, N, and Rb. So we have cobalt, and we have nitrogen, and we have rubidium. So the trend is, as we go across, they get bigger. So nitrogen smallest, CO, then Rb. Do they want it in? Oh, from largest to smallest. So Rb, CO, N. Rb, CO, N. Why did I place them in this order? Because, well, let's just put the two reasons. Decreasing the number of shells decreases atomic radii, and increasing number of protons, also known as nuclear charge, decreases the size, decreases atomic radii. Whew. Okay, so let's continue from there. Ionization energy of an element is the energy required to remove an electron. As you go across the period, ionization energy increases or decreases. So we're going to continue to go left to right, even though it doesn't specify. If it doesn't specify it on the test, you better ask. If I go from left to right, ionization energy increases. As I go down, ionization energy decreases. And again, the reason that is, as I go from left to right, okay, I'm going to draw an electron on fluorine, and I'm going to draw an electron on lithium. Lithium has 3 protons, and because of that, it lets this shell get way out here. So how hard is it to sneak this electron off of lithium? Well, first of all, lithium only has 1 valence electron, so it's real easy to sneak that one off. Second of all, it's further away from the nucleus, so it's real easy to sneak that one off. Third of all, this only has 3 protons, so it has a reduced nuclear charge, so it's real easy to sneak that electron off. Now let's look at fluorine. Fluorine has 9 protons, so that makes it harder to pull an electron off. It has 7 valence electrons, so it's trying to pick up another one, so that makes it harder to pull that electron off. And look how close that is to the nucleus, to the positive charges. This electron is very close, so that makes it harder to remove that electron. So first ionization energy increases as I go across. Okay. Place the following in order from highest to lowest ionization energy. So we have cesium, and this is what I want you to do on the test too. I want you to put them in order. We have cesium, we have lithium, and we have sodium. So ionization energy, the trend is opposite of atomic radii, so I'm going to draw that on my periodic table. This is atomic radii. And then I'm going to draw another periodic table. And I'm going to draw this upward to the right trend, and that is ionization energy. That is also electronegativity, which we will get into in a minute. Okay, so as I go up, electronegativity increases. They want from highest to lowest. So I'm going to start with LiNaCS. LiNaCS. CS has the lowest. So I went from highest to lowest. Why did I place them in this order? Okay, so when I'm adding shells, I'm adding what's called electron shielding. basically this center positive charge can't see the electrons as well on the outside shells because this gets much bigger, right? So it can't see those electrons on the outside, so it's easier to remove them. Whereas this only has 2 shells. It's very easy, very hard to remove. It takes a lot of energy, ionization energy, to remove an electron because it's right beside this. It's right beside the nucleus, the positive charge, so it's harder to remove. This down here, cesium, has 6 shells, so it's got 5 shells in between the nuclear charge in the center and that outermost electron, so it's easier. That's why. So, why did I place them in that order? Increased electron shielding. And you could say this the opposite too. I'll tell you how to do that. Increased electron shielding decreases ionization energy. Ionization energy. Energy. And I'm going to write one other thing here. Increasing numbers of shells increases electron shielding. Now I could have said decrease electron shielding increases ionization energy. You can say any of these things opposite of each other. That doesn't matter. But for now, I'm just going to put one answer so that you understand increasing electron shielding decreases ionization energy, and that increasing the number of shells in the way increases that electron shielding. So I hope that makes sense. I'm going to end part 1 now, and I'm going to start part 2 momentarily.